Hello everyone, my name is Lingyu. I'm very glad to be here, and this is a joint work between RPI and NEU. I'm from RPI. Let me introduce our paper to you. Okay, so our work is developed for a group meeting scenario. We assume that participants' body language can reveal important information about their personalities, and these personalities are closely related to their job performance, motivation, and creativity. So we want to build a system for automatic personality traits screening. To do this, typical measurement for body language is based on the frequency of the visual events. For example, for body behavior, we would measure the fraction of time that a person has large body movement. Well, one question is that human behavior is too complicated to be described by a single frequency of a single event. One's behavior during the interaction can be affected by others' behavior or others' response to your behavior. Therefore, to better model the interaction between group members, our main contribution is to measure the co-occurrent event. So, for example, we would measure how frequently a person will move her arms when she's the focus of attention of the group. We propose that the combination of this can help better model the group interaction. So we would extract the, we would extract the co-occurrent events for each pair of the individual events and then measure the correlation prediction analysis. So we measure the visual focus of attention for facial features. We design a neural network based on head pose and eye gaze to classify the visual events on a frame-by-frame basis. For hand features, we estimate the relative hand and face position based on facial landmarks and hand bounding blocks detected by a convolutional neural network. For movement features, we measure the motion intensity based on frame difference and number of moving body parts based on motion history image. To understand the feature importance, we measure the correlation between feature and outputs. Take extroversion as an example. Multiple body parts moving while receiving attention has strong positive correlation with extroversion. This is in line with the existing finding that extroverts can be motivated by social rewards. For prediction, we can see here, the combination of the co-occurring events can help better model the interaction cues between group members, and our method achieves state-of-the-art accuracy for predicting the personality traits. So thank you very much for your interest and attention. Our poster board is 26. Let's discuss it later. Thank you.
Hello, my name is Nemanja Djuric, and I will present our work on uncertainty-aware short-term motion prediction of traffic actors for autonomous driving done at Uber ATG. To ensure safe and efficient operations of a self-driving vehicle, we need to reason about future motion of vehicles in its surrounding, as well as the uncertainty of that motion. This prediction task is a topic of our current work. To develop a good prediction system, model needs to take into account map constraints, as well as all the other actors in the scene. In this example, we have an actor of interest, colored yellow, taking a left turn in the intersection. And their behavior is affected by all of these factors. However, it is not really clear how to present this information to the model. Some earlier work proposed to manually define useful features, such as distance to the road edge, distance to the crosswalk, distance to the nearest actor. However, this is clearly suboptimal and time-consuming. As an alternative, we propose to generate bird's-eye view raster images of the scene that would encode all of this information. Here we can see the resulting image for the previous intersection example that arguably contains all the contextual information necessary for good motion prediction, such as lane boundaries, lane directions, historical positions of actors in the surrounding, and so on. Then we can take this raster image and use it directly as an input to the deep model. In addition to positions, we also model uncertainties by assuming that positions are sampled from a Gaussian distribution. Then we can train a model by maximizing log likelihood of the training set by taking future positions every 0.1 second up to 3 seconds in the future as labels. And since the input is simply a raster image, we can directly use CNNs to extract useful learned features, followed by a couple of fully connected layers that eventually output XY positions and uncertainties. Here we see an example output for a fully trained model. In top left, we see a raster image for an actor making a right-hand turn in the intersection. Overlaid is the ground truth trajectory in green, and blue is our output trajectory. You can see that it very closely and accurately follows the ground truth. In top right, you can see that our output uncertainties are also very intuitive, as the actor can take any of the two available lanes as they complete the turn. In addition, we can also generate other useful and interesting visualizations, such as model uncertainty, sensitivity analysis, and so on. And we can discuss these more at the poster. Here we just saw a glimpse of the capabilities of the proposed model. Please come to our poster for a more in-depth analysis that includes a comparison to other state-of-the-art baselines, uncertainty calibration plots, ablation study, and much more. Thank you very much for your attention.
Hello everyone, I'm Willie Brink from Stellenbosch University in South Africa, and this was work mainly done by my former student Peter Thompson. The plant genus Protea is a poster child for the biodiversity in South Africa and very important to monitor for the sake of conservation. So the aim of this project was basically to identify the species of Protea from crowdsourced images with optional location and date attributes. It's a challenging problem because the images were taken in the wild by many different people. There is also a very big class imbalance in the data available for training and testing, and we should expect big variation in images of the same species, as well as possibly strong similarities in images from different species. So we collected a data set of roughly 5,000 images across 41 species, and we also built conditional probability distributions over location, elevation, and flowering times, which are discerning qualities of these species. Our proposed identification model consists of 3 parts. Firstly, it's a standard CNN, where we also built in a multi-region attention mechanism to hopefully focus on the flowers in the images. We then have a second CNN that exploits the hierarchical taxonomy of flora and classifies images on a coarser subgenus level that we then probabilistically expand down to species level. Finally, we have a probabilistic model that combines the output of the 2 CNNs with the likelihoods of any observed location and date attributes. Here you see some test results from our model, as well as a few baselines and various variants of our model. We show the top 1 and top 3 classification accuracies, as well as recall, which in this case is mean per class accuracy. Our full model outperforms the baselines as well as all other variants. The graph on the right shows accuracy per species, and the species are ordered from left to right by the number of available training images, so we see no discernible decrease in depth. Our paper also contains a few other experiments, like this one, which shows the effect of different attributes on the top 3 classification scores, and we see that location and elevation, for example, is very useful for the discerning of Proteas specifically. Thank you very much for your attention.
Hello. Hello, here I will present the reverse variation autoencoder for visual attribute manipulation anomaly detection. My name is Lydia Gauerhof. So you see already by the title that there are 2 main applications for this one model. First is the visual attribute manipulation. We can also combine these visual attributes when generating images, and we can detect anomalies, so whatever is a deviation from the data space used for training. So how does that work? We have like the generator that takes the stochastic Latin vector as an input and maps that to the data space. And meanwhile, the encoder takes the generated images and reconstructs the Latin vector. Generator and discriminator are trained adversarially, and the discriminator learns by this way to distinguish between generated images and real images. So, and the overall model tries to match the Latin data space joint distribution of the generator and the encoder by minimizing the Kullback-Lieberg divergence. So we have some results here. First of all, in A, you see some randomly generated images, the 4 images. In B, you see the reconstructions of the first column. In C, you see the image in painting. So if you put some part of the image out of that, you can reconstruct that. And the image morphing from the left image to the very right image. So you have a blending of these images. And here are some combinations of visual attributes. So you can just disentangle like one single attribute, but you can also take a lot of different attributes and combine them. So in the very left column, you see the original image, and then you can add by generating images, like in the second column, smile and black hair. And like the other columns have other different visual attributes that you can just add and combine. And this is very nice to have like different data. And here you see the results about the anomaly detection having this state-of-the-art performance, and you see like very clear for the anomaly number 1. It's really hard to detect number 1 because it has the same features as other numbers have. For example, the strike of 1 is already included in number 7. So yeah, we have other results to discuss. Please come to the poster at 28, and I'm happy to meet you. And once again, reverse VAE for visual attribute manipulation and anomaly detection. Thank you.
Hello everyone, my name is Jun Nagata from Keio University in Japan. My research theme is QR code reconstruction from event-based camera. Event camera is bio-inspired vision sensor that asynchronously output per pixel brightness changes as event contain timestamp, pixel location, and polarity. If there are no motion, no event are generated at all. Conversely, even if the motion is very fast, event camera does not suffer from motion blur. The asynchronous nature of event camera offers several advantages over traditional cameras, such as high temporal resolution, high dynamic range, and low latency. This is a scene of a fast-moving QR code. The left is event accumulation, and the right is a video captured by iPhone in slow motion mode. While the 240 FPS camera suffers from motion blur, event camera can capture clearly. Our research goal is fast and robust QR code reconstruction from event data, assuming the factory automation that needs robustness against light condition and motion blur. And the key idea of our method is that image is modeled to be generated by affine transformation of the QR code. And the reconstruction problem is solved in the constrained QR code space. In conventional methods, the whole image is reconstructed under the smoothness assumption. On the other hand, in our method, the QR code is directly reconstructed by optimizing in QR code space. Here is the reconstruction results, left to right. The input event, the image captured by 330 FPS camera to conventional method and errors. This is a demonstration of QR code reader assuming the entrance gate. If you want more information, please come to the poster number 29. Thank you for your attention.
Good evening, everyone. So I'm Tsung-Han from IIIT Hyderabad, and I'll be presenting the work of end-to-end person recognition on behalf of my colleagues at CVIT Lab IIIT Hyderabad. So facial cues are commonly used for person identification. However, in many practical scenarios, identification from facial images is not always feasible due to extreme pose, occlusions, or non-visibility of the face. So in such scenarios, it is important to consider other body cues that provide complementary information for recognition. So current works for full body person identification aim to learn feature representation for different body regions and train a CNN for each body region. However, there are two shortcomings with this approach. Training an ensemble of models for the same task is suboptimal. It is also slower and requires extremely large number of parameters. Also, these models combine features or classify scores with nice strategies such as concatenation and averaging, which is not effective as it weights each body part similarly irrespective of the discrimination ability. So in this work, we propose an end-to-end person recognition architecture in which a single convolution neural network is designed to produce a compact representation. Our architecture consists of 3 essential blocks. The first block takes a complete person image as input and produces convolution feature maps. These feature maps are shared across multiple body regions and hence require only a single forward pass to compute. In the second block, features are pooled from multiple locations of the shared feature maps according to predetermined region of interest inputs to obtain an intermediate representation for each body region. Finally, the aggregation block maps the pool features into a low-dimensional space and combines them with adaptive weights produced by the attention module. The parameters of this module can be trained in an end-to-end manner with network parameters. So as shown here, the attention weights corresponds to the discriminative ability of the body regions. So whenever a particular region is occluded or not clearly visible, as we can see in the images, the corresponding weights are small. And similarly, large weight is given for discriminative body regions, which are clearly visible in the images. Moving on to the results. On Piper dataset with our RCNN approach, we obtain a similar performance for different body regions compared to training them separately. Also, our attention method improves over naive fusion with averaging. So we experimented on Piper, Hannah, and Soccer movie datasets and obtained consistent improvement over previous methods with a single model as opposed to an ensemble of separately trained models. Our method required far less number of parameters. That's it. Thank you. Please visit our poster 449.
Hello, everyone. I'm presenting on behalf of my college at the University of Adelaide. The paper is about event-based star tracking using hub transform. So what is star tracker? So it's an optical and computational device that exploits the fixed pattern of the star so that it can reconstruct the 2D and 3D correspondence. This step is very expensive in terms of computation. And then it can solve the Wabash problem to obtain the camera orientation, or in the other word, the attitude of the satellite that the camera is attached to. So the motivation of this work is satellites are the resource-constrained devices, and they are becoming like smaller and smaller in size. So we need to track its attitude efficiently and effectively. And ACE event camera is well known for its energy efficiency and higher dynamic range. So that motivates for our work. So on the top left is the 2D star button. On the top right is the X, Y, and T button generated by the event camera. And on the bottom right is the 3D line detected by using Hubble transform, and then we projected the motion of the star on the bottom left. So if we know that the end of the motion of the star, we can track the attitude of the satellite. So our proposed pilot is we use the relative rotation estimation from the event-based camera within multiple time steps, and then we combine with the absolute rotation estimation, which is very expensive, but we're sampling it at a very lower sampling rate, and we combine those two to optimize the estimation for the camera orientation. So in the next slide, we demonstrate the capability of our proposed method. So on the left, you can see that the green one is the route truth of the camera. The blue is the one, the initial change attitude, and ours is the red one. So if you look carefully for the blue one, it's very sensitive to noise, whereas the red one is much more robust. So in conclusion, we are the first one to propose to use the event-driven camera to track the attitude of the camera using a multi-resolution asynchronous Hubble transform. And thank you for listening.
The name of my work is Toward Explainable Fashion Recommendation. My name is Pongse Tangseng. This work was done while I was a PhD student at Tohoku University, Japan, under the supervision of Professor Takayuki Okatani. My works tell you how your outfit is bad or not, and point out exactly what to improve. The goal of my work is to create a model to give a score to any outfit, and be able to point out the flaw so the user can improve it. My scoring model is trained on 200,000 outfits from now defunct fashion-based social media platform called Polywar, which has likes and comments and lists of items. I use outfit with likes as positive samples and randomly created outfits as negative samples. Each item is separated into main colors and shape and texture. The features are input to the model. The model is trained as a binary classifier. We then backpropagate the gradient back to each feature to identify its influence on the badness of the outfit. We show that our work can identify the flaw in an outfit effectively. According to our evaluation, our method is able to detect the feature level flaw in an outfit with accuracy around 90%. Thank you very much for your attention. Please see our work in detail in the poster session. My paper number is 428. Thank you very much.
Hello everyone, I'm Yishan Fang from National Jiao Tong University, Taiwan. Today I'm going to introduce our work of self-contained stylization via steganography for reverse and serial style transfer. Typical style transfer approach aims to transfer the style of the content photo according to one of the reference styles image. However, The problem of the reverse style transfer for removing the stylization of a stylized image to recover the original content photo is rarely discussed. Also, no prior work has discussed the problem of a serial style transfer, which transfer a stylized image into another style but preserve the content of the original image. None of the existing methods can easily tackle these two problems, where the original photo and its stylized image has content inconsistency due to the stylization. To resolve the content inconsistency, we proposed to integrate the idea of the stereography with the style transfer, where the content information of the original photo is heading into the stylized output. We have two methods proposed in our paper, and one of them sequentially perform the regular style transfer. Then using an encryptor to hide the content feature of the original photo into the stylized image without making sufficient change on its appearance. With having a decryptor joining to well retrieve the hidden content feature from the encoding image, we are able to use some content feature to recover the original photo or transfer it into another style, thus achieving the reverse and serial style transfer. Here come some results. Given the content and style images, our model can well perform the typical style transfer with the content feature seamlessly hiding in the results stylized image. And we are able to easily reconstruct the original photo solely based on this encoded stylized image. Our model can perform multiple style transfer in the series without requiring the original content photo. Thanks to the power of the stereography, even after many types of the style transfer, we can still clearly observe the structure of the original photo in our resultant stylized image. Please visit our poster to know more detail and have a discussion with us. Many thanks for your attention.
Hi, I'm Daiki from the IBM Research AI. I'm going to present the robust anomaly detection with the Zhang. So first of all, our target application is automating the medical hand imitation test for the dementia. So the doctor make this pose, and then the doctor will say that please imitate this pose. But some dementia person cannot do this kind of stuff. So we want to do that kind of anomaly detection using that kind of stuff. So the research question is, can we get such kind of attention from the Zhang? So to do that kind of stuff, so we proposing that the adversarial discriminative the attentions. So this is that how do we train the network, and then this is that how do we get the anomaly score from that attentions. So, and in the experiment, we also train on that MNIST, and this is that how the training works. And this is that our data set works. I mean, the Zhang is training about that, the posing. And this shows that the attention is going to be training. So after some iteration, the attention is focused on the digit area in this MNIST. So yeah, and then this is our data set. And then attention will going to be focus on to the hand regions. And this shows us the comparison table. So our method has the best result in all other state-of-the-art methods. And finally, this is that how the attention or other the images will work. So, and from the left, so this is the input, and then the next one is the reconstructed the images, and the next one is the difference, and then the fourth one is the attentions, And then the fifth one is that weighted from the attention, weighted the difference from that attentions. So, yeah, we want to discuss about it more detail at the poster. Yeah, this is a movie. So that means that the attention can focus on that hand reason that we are proposing. Yeah, that's it. Thank you.
Hi, I am Ayush from the MDSR lab at Adobe. We'll be talking about our work in image-based virtual try-on. So the task of image-based virtual try-on, in a sense, involves taking as input the image of a target model, a new in-shop cloth, and swapping in the cloth on the model to generate a final try-on output. So a standard pipeline in general consists of two phases. The first phase involves transforming the in-shop cloth to align with the pose of the target model, generating a warped cloth. In the next phase, the warped cloth is transferred onto the target model to generate the final try-on output. In this work, we propose SieveNet, a novel framework for doing image-based virtual try-on, and we break down the entire process into 3 components. So we first introduce a coarse-to-fine warping strategy. Then, to do better texture transfer, we introduce a conditional mask prediction prior that is used to do a segmentation-assisted texture translation. These correspond to our warping and texture transfer phases. So this slide explains the architectures for each of them, and I'll be talking about them in detail. So yeah, to better model fine-grained intricacies during the warping process, we regress the parameters of the spatial transformer network that is used to warp the cloth hierarchically in multiple phases. However, at inference, we use a single cumulative spatial transformation to generate the try-on output. And we train this with a geometric matching loss that we introduce, and we'll discuss it in the poster later. Next, to handle better artifacts during the texture transfer process, we break down the process into 2 steps. A conditional mask prediction step and a segmentation translation step. So in conditional mask generation, we predict the resulting segmentation mask of the model after the try-on output and use this as a prior to constrain the final texture transfer. So this helps in better modeling artifacts such as bleeding and occlusion in the final try-on output. So to do the final texture translation, we take as input the conditional mask segmentation predicted in the previous step, the warped cloth predicted in the first step, and a couple of translation priors. These are components that remain unchanged during the during the try-on process and should be preserved. We use this to generate the final try-on output. And we train this network with something we call a dual-link triplet strategy, where we use past parameter states to regularize the training step. And this helps us in handling preserving better artifacts, such as arising from problems like bleeding and occlusion. We baseline experiments with CP-Buton, which is a recent state-of-the-art method, on a wide range of metrics of image quality. And our results show that we significantly outperform them on all metrics. We also conduct extensive qualitative analysis of our method on a wide range of parameters. We see that a proposed method is able to generate better quality of image by preserving the bottoms, handle occlusion more effectively, generate skin regions more precisely, as well as handle large variability in poses. Thank you.
Hello everyone, my name is Amélie, and today I'm to talk about our project on transfer learning for visually dissimilar domains. So when we talk about transfer learning, often people would think about fine-tuning, which is pre-training on some source task and then tuning the later layers on the target task. So often the underlying assumption here is that feature extracted by neural network transfer well across different image domains, in particular early layers. And so this has been, of course, used for many applications, for instance, pre-training some classification network and transferring for tasks such as detection or segmentation. However, this is often true when the visual domains are similar, for instance, natural images. And it's not really well known whether transfer learning is still beneficial, whether domains are dissimilar. So this is exactly what we try to target here. We look at settings where we have domains which are dissimilar visually, but have similar semantics. So because we have dissimilar visual domains, the assumption that early layers are similar breaks. So the alternative would be to fine-tune every layer, but of course this is not always possible. For instance, when we have data scarce settings, then we have the risk of overfitting. So instead we want to kind of investigate whether it would make sense to instead tune intermediate units in the layer to recover the representation from the source domain. So first to do this, we want to just investigate it with a simple model selection criterion. So we take our Protea source network and just tune every layer on the target task and pick the best layer based on validation accuracy. So what we observe first is that in several settings, it's not always obvious that fine-tuning the last layer is the best situation. And secondly, that the pattern on which layer we should tune is not always obvious. It depends on the amount of data available and also the kind of shift that we have between the source and target domains. So the problem with this model selection criterion is that it's very slow, right? Because we would have to tune a model for each possible layer. So we also propose 2 faster variants, where the high-level idea that in the end we do not want to have fully trained networks, but we just want to have an idea on which layer is actually the most promising to tune. So these 2 methods are faster in the sense that we only need to train 1 network. Then we basically evaluate all of these selection criteria on different domain shift settings and also different data scarcity scenarios. And from a high-level perspective, the insight that we have is that first, in many scenarios, it's more useful to tune an intermediate layer than the last one. And this is particularly true when we have local pixel level changes. And also on large architecture, this method is a bit more efficient than fine-tuning all layers because it's less prone to overfitting. And yeah, finally, I just need to show you some qualitative results on which kind of layers is picked by the different selection criteria. And yes, of course, if you want more details, please read our poster, which is poster number 36. And thank you for your attention.
Hello everyone, my name is Chou. I'm presenting our work, Multi-Label Visual Feature Learning with Attentional Aggregation. This is a collaboration between Stellenbosch University, Brookhaven National Lab, and New Jersey Institute of Tech. Our work aims to improve the annotation of X-ray scattering images in material science, examples shown here. From the images, we're going to deduce some material attributes, which are basically a wide range of checkboxes that are not mutually exclusive. And our goal is to improve the prediction based on a box standard CNN. So, a standard CNN does not work well with these image features because they can be spread out and scattered, shown in A on the left, or pretty weak, shown in B in the middle, or overlapping, shown in C on the right. This inspires us to do some local to global refinement to pick up the weak spots and to reorganize the spread out features effectively. We introduced the attentional aggregation module for this task. As we can see here, the AAM is an adding block in the ConvNet. The attention module, which is the yellow box in the figure, flows through the network, and the aggregation module, which is the red box, leads to side output. Let's discuss in more detail. The attention module has 2 attention maps by multiplication in succession, one multiplying on the channels and the other on the spatial dimensions. For multi-label annotation, we generate P distinct spatial attention maps and apply each of them to a slice of the convolutional feature maps. These multispatial maps are trained with different groups of prediction attributes, so they are pushed to diverse. The aggregation module is basically a bag of words as shown here. The cluster is done with softmax, so it's differentiable in backpropagation. The aggregated features then go straight to a separate attribute prediction. This is the same idea as in Google Alert. Like what we have in the middle, we just predict with them, so that we make sure the mid features are structured and meaningful. We have done experiments to show AAM is effective to enhance image features. For ablation studies, we tested the base network, VGG16, and plus aggregation, and plus attention on synthetic dataset, which indeed improves mean average precision, or MAP. Also, our attention method works the best amongst the comparisons. In transfer learning on real experimental data, we compare our method with some deep learning models, and in particular, with attention methods like squeeze and hesitation network and residual attention, shown here. In conclusion, we presented the attentional aggregation module, a local to global image feature enhancement method. Please come see our poster for details. Thank you.
Indian Institute of Technology, Hyderabad, and I'm here to present the paper, Charting the Right Manifold Mix of a Few-Shot Learning. This was a collaboration with Adobe Research India. Few-shot learning, all of us understand, has a training phase where you learn over base classes with abundant labeled examples. and then you have an evaluation / fine-tuning phase where you learn an n-way classifier on unseen novel classes. So existing approaches can be broadly divided into transfer learning as a trivial baseline, meta-learning based methods like MAML, distance metric methods, and hallucination-based methods that use GANs to generate examples from the few shot samples. Our key contributions in this work is twofold. One is to show that manifold mix-up regularization over a feature manifold that's enriched using self-supervision is significantly useful for few-shot learning using just a simple inference machine. And the proposed methodology outperforms state-of-the-art methods by 3 to 8% on CIFAR-FS, CUB, mini-ImageNet, and tiered ImageNet datasets. So manifold mix-up was a paper published in ICML of 2018, which leverages linear interpolations in the feature spaces and corresponding interpolations in the label spaces to be able to learn, to be able to minimize what is known as vicinal risk. And rotation self-supervision, which is one of the self-supervision losses that we used along with exemplar loss, simply rotates an image and asks the model, asks the network to predict the rotation class. So this was one of 2 self-supervision tasks we used in our work. The proposed method is called S2M2, stands for self-supervised manifold mix-up, where we initially train with rotation self-supervision as an auxiliary task, then we fine-tune with manifold mix-up for a few more epochs, where we combine the manifold mix-up loss along with the rotation self-supervision loss and the classification loss. These are the results. We have many more results in the paper, but these results show that we outperform state-of-the-art results, state-of-the-art methods by 3 to 8% on multiple data sets. We also tried varying n, which is the number of classes in which you have a few shot setting, going all the way until 20. And in all of these situations, we show that we outperform existing methods despite a very, very simple inference engine. We also try cross-domain few-shot learning, where we train the base model on mini-ImageNet and then fine-tune it on CUB. Here, once again, we show better results on baselines. To conclude, we summarize that relevant regularization along with self-supervision leads to a better feature representation that can be useful for few-shot learning. If you're more interested, please stop by our poster. Thank you for your attention.
Hello, everyone. This is Patrick speaking. And my topic today is measuring the utilization of public open spaces by deep learning. Nowadays, people care more and more about their health. And the concept of healthy living does encourage people to stay physically and socially active, while public open spaces in cities are good platforms for people to take such activities. Well, that leaves us a few interesting questions. For example, how does the community use its public open spaces? Where should the park investment be directed in the future? In the realm of urban planning, people are still using traditional methods to study the public life. They are both time and labor consuming. In order to solve the issues, I built an automatic people sensing framework to achieve detection, tracking, mapping, and counting. My benchmark study is carried out at the Detroit Riverfront Parks. I use the installed camera network and expanded it into people sensing system for urban studies. I built a custom dataset, OPUS, meaning objects in public open spaces. It includes annotations of 10 classes of people with various activities on different illumination conditions. I use MARSC RCN as a detector and OPUS datasets for transfer learning. Here are some detection results. The detection performance is very consistent throughout different cameras. The table on the top shows the evaluation results for different classes, and the bottom figures shows the precision recurrent curves. In order to know the exact location of the detected person, I built a mapping module so that I can achieve activity mapping and study the utilization of the place over a long period. For example, the figure on the bottom left shows the cumulative scatter plot of the users in a week, and the figure on the right shows a corresponding density map. Psychologically, people like to stay around places with features because they can feel safe and comfortable. I also built a tracking module using tracking by detection paradigm with common filters as trackers and a Hungarian algorithm as data association method. By using the sensing framework, we can know at any specific time how many people are on the pathway, where are they located, and in which direction are they moving. A lot of such useful data can be collected for urban studies automatically. That is my talk. Thank you for your attention.
Good evening, my name is Jan. I'm from the University of Tokyo, and today I'm going to present our paper titled Erasing Scene Text with Weak Supervision. Our task is to remove any text from a given photo. That means we take an image with text as input and generate a natural-looking image without text, as you can see in the video. One of the motivations for this task is to conceal private textual information in image data, such as license plates, house numbers and name signs, and so on. An example of protecting such data in real applications is blurring some text information in Google Street View. Existing methods that focus on erasing text from images consider the task as end-to-end image-to-image translation. However, that requires corresponding pairs of images with and without text. Such data is impossible to easily obtain from real photos. Some works use synthetic data to overcome this problem. We divide this task into two subtasks, scene text detection and image in painting. The two modules are trained separately and joined at inference time. Detected text regions are masked out from the input image and repainted using an image in painting model trained on a large-scale image dataset. This way, we don't need images without text for training and only need text region bounding box annotation to train the detector. This is the overall view of our model at inference time. The scene text detector produces a binary segmentation map of detected text. This map is used to mask out the text regions in the input image. And after that, the masked image is passed to the in-painting network that fills in the masked out parts. Here you can see some examples of images where the text was erased using our model. So first, we evaluate our method and compare it with existing methods by how much text remains in the produced images where text has been erased. All of the methods here use the same scene text detection model for evaluation. It is trained on the IGDAR 2013 scene text dataset, and recall is used as measurement of how much of the text in the original images is still detected in the generated images without text. We also measure and compare the visual quality of the generated images using structural similarity and peak signal-to-noise ratio, and the results show that our method yields competitive results without the need of image pairs for training. For more information, please drop by poster number 42. Thank you.
Top left, that's me, Shreyansh Gandhi, and will be presenting scalable detection of offensive and non-compliant content. Product images are super critical for good customer experience, but non-compliant images like the ones around nudity, sexually explicit, assault rifles, or toys that look like it are a problem. Now, which product would you choose from the four options? Mostly the second one. Third-party sellers can put bestseller logos to get more clicks, or they can use any one of the other marketing logos shown below. The paper talks about how we find and get rid of these various non-compliant images. We present the different technical challenges we overcame. First, as you can see, there are a variety of logos even for a single use case, making it hard for the model to generalize. Second, the catalog is massive, more than 100 million products. It's diverse, more than 10,000 product categories, and it's constantly changing. Offensive content can appear on products across all categories. This adds to difficulty in training models. Third is fine-grained classification. Hunting rifle is fine, but assault rifle is not. Fourth is lack of training data. Non-compliant images are like needle in haystack. Even if we collect images from various sources, at best we have hundreds of labeled data points. In this paper, we present different strategies for building training data, one of which is using visual search to get more positive samples and very good negative samples. For the logo problem, we use novel synthetic data techniques to generalize our models across various forms of a single logo. We describe the various model training approaches. As you can see, A, training a classifier on deep embeddings from a model which is trained on entire catalog images. B is fine-tuning varying numbers of inception and ResNet blocks to find optimal performance. And C is object detection. And finally, we discuss the iterative framework we followed, which allowed us to start from a handful of images and build a production-ready model for a massive and a diverse catalog, and how all these things come together in production running over 200 million images through it. The strategies adopted and the insights gained can be leveraged by any content-serving platforms from other domains which need to enforce their trust and safety guidelines or their terms and conditions. Thank you.
Hello, everyone. I'm Yan Chen from SenseTime. I'm going to talk about our work, Very Power-Efficient Neural Time of Flight. Nowadays, 2F cameras are becoming increasingly popular for active depth sensing. However, the quality of depth generated by traditional algorithms degenerates rapidly with the decreasing illumination power. Thus 2F imaging has to face a painful dilemma for the illumination and the performance trade-off. To tackle this dilemma, we propose an end-to-end pipeline to translate the weak and noisy 2F camera raw to high-quality depth map. As shown on the screen, depth image A and C are produced by the 2F camera's default imaging pipeline, and we can notice that depth values of distant objects and black objects in the scene are invalid, while our method can fill invalid areas with accurate depth values, as shown in image B and D. Traditional 2F imaging algorithm always suffer from severe noise and MPI errors when the exposure time is low, or there are objects with low reflective in scenes, while our end-to-end convolutional neural network can generate high-quality depth images directly from very weak 2F raw data through a learning process. Besides, we also collected a comprehensive dataset under a variety of scenes used. For training and validating this learning tasks, we use a specialized 2F camera with raw data access, EPC 660 2F camera, to collect a dataset of multiple pairs of short exposure and corresponding long exposure depth measurements. Architecture of our network are UNet-like, and we propose a new loss, named 2F loss, consisting of loss based on raw measurements and depth value for depth reconstruction. Here are the experimental results. Compared with traditional algorithms, our method greatly increased the MAE and SSIM of results. Therefore, we show in the experiments that it is possible to devise a deep learning model to recover high-quality depth from very weak and noisy 2F raw measurements. Please come to our poster for the details. Thank you.
Good evening, everyone. My name is Amina Khatun. I am from Queensland University of Technology, Brisbane, Australia. I am going to present my paper, Semantic Consistency and Identity Mapping Multi-Component Generative Adversarial Network for Person Re-Identification. Actually, person re-identification is the task of matching pedestrian across different locations over multiple camera views, such as determining whether the person observed by camera 5 is now the same person visible in camera 4. It is still challenging to re-identify the target person accurately in the presence of domain variations. Thus, in a real-world scenario where the domain of the target images has no overlap with the gallery images, performance is severely reduced. To address this problem, cycle GAN is widely adopted to transfer the style from camera to camera or domain to domain. However, cycle GAN can only transfer images between two domains at a time. In contrast, our proposed method is able to generate images with multiple styles at a time, all with the same identity as the original image. If we have 4 domains, thus to transfer the style among these 4 domains, cycle GAN requires 12 generator discriminator pairs, whereas our proposed method requires only 4 generator discriminator pairs. So this is the architecture of our proposed method. Here we use identity mapping laws between the real and the generated images to ensure that the identity of the transferred person is the same as the original image. However, the cycle consistency loss and the identity mapping loss are used at pixel level and as such fails to capture the semantic features shared across domains. This leads to a drop in performance when domains are vastly different. To address this limitation, we propose a semantic consistency loss operating at the feature level to ensure that the semantic features are preserved for both the input and the style transferred images. For the re-identification task, we adopt joint verification identification approach with an improved quartet loss, which enforces the network to minimize the intra-class distance. We used 6 datasets to evaluate our proposed method. For all datasets, we outperform the state-of-the-art approaches significantly. So these are the generated images in 6 domains of our proposed method and cycle GAN. Compared to our method, it is harder for cycle GAN to generate the images preserving the identity as the original image. From the TSNE visualization, we can see that the proposed method with the improved quartet loss optimizes the embedding space such that the data points with the same identity are closer to each other than the traditional quartet loss. If you have any question and for more details, please come to the poster session. My paper ID is 1037.
Hello everyone, I'll be presenting our work titled Structured Compression of Deep Neural Networks with Debiased Elastic Group Lasso. The authors are with the University of Luxembourg. Here is the outline of the presentation. The objective of the paper is structured model compression, where we compress a large model into a small one by eliminating whole filters or hidden units. Figure 1 shows the general framework for structured compression, starting with the original full model to identify redundant convolution filters or units, to remove such filters or units using a specified weight threshold. Lastly, the prune model can be retrained to realign the remaining model parameters. In this slide, we discuss the use and challenges of group lasso for structured sparsity. The formulation of group lasso penalty for structured sparsity is given in the equation. However, for compression, group lasso has the following challenges. First, group lasso does not select more parameters than the number of training samples. And second, when there is feature correlation, group lasso randomly selects a group of features such that there is unstable feature selection in different runs. Third, group lasso performs both parameter selection and shrinkage, in contrast to our main interest in feature selection. In this slide, we show what we propose to overcome the difficulties earlier mentioned. First, we employ group lasso for enforcing structured sparsity. Second, we employ L2 norm to promote feature grouping and improve feature selection stability. Third, we debias the model by eliminating group lasso, such that the problems of saturation, instability, and entanglement are alleviated. The formulation of elastic group lasso used in the paper is shown in the equation. In this slide, we show some of our results for different experiments. We evaluate our models on increase in error rate, the parameters of models burned, and the reduction in number of flops. We performed experiment on popular HalexNet and image recent 50 using the ImageNet dataset. Results are shown in bold, what we propose, and in comparison to the state-of-the-art models, we are able to prune more parameters with lower error rate. In this slide, we show on HalexNet the filters, number of filters and units pruned for the different layers in the HalexNet. Also, we show how the different pruning threshold affect the performance of our proposal. Then we see that our proposal also performs the group lasso. In conclusion, we revisit the drawbacks of group lasso for model compression. We tackle the identified problems. We evaluate on ResNet 50 and HalexNet. Thank you for listening, and if you have more information about our paper, please see the post at poster 46. Thank you.
So good evening, everyone. I'm honored to present work of my group mates, plug-and-play rescaling-based crowd counting in static images. So in this research, they aim to count number of people in static images in extreme low to high density scenarios with equal effectiveness. And crowd counting is an integral part of crowd analysis. With huge crowd gatherings during social, musical, and political events, it can lead to effective and better management of such events and prevent any unwanted incident. We know the challenge of crowd counting now should lie in the huge variance in scale and image resolution, the large perspective, severe occlusions, and dense crowd-like cluttered background regions in the images. So to address these major issues, we propose a simple yet effective image patch rescaling module and 3 new crowd counting frameworks using the plug-and-play PRM module. And the PRM module is used to rescale the input patch by utilizing one of the 2 rescaling operations, the upscaler and downscaler. So based on the prior estimated crowd density class CP, the PRM module rescales the input patch, P and LC, using one of the its rescaling operations, namely the upscaler or downscaler, and generates 4 or 1 new rescaled patches respectively. And the MC labeled patch bypasses any rescaling. So this simple yet effective plug-and-play PRM module helps in catering the huge crowd diversity challenge. And we then also designed the 3 new architectures employing this plug-and-play PRM module. And the modular crowd counting scheme CC mod, as shown on the left, the input patch is first classified 4-way, followed by passing through the PRM for any rescaling, and then go through the crowd count regressor for final patch crowd count CCP. So whereas in 2 end-to-end crowd counting networks, they couple the PRM module with the base network to address the huge crowd diversity issue. And we see that we present a few qualitative results consisting of actual test images from different benchmark datasets. And our method yields better and closer to ground truth performance as compared to other recent state-of-the-art regression and density map estimation-based methods. And we also compared the schemes with other state-of-the-art methods on 3 benchmark datasets, and our methods performed the best on root mean square error, evaluation metric, and the other mean absolute error. So that's the work. Thank you.
Hello, everyone. So we are Amin Trabulsi and Mohammed Shaben, PhD students at Colorado State University, working with Professor Radosavljevic and Professor Nate Blanchard. And today we are presenting our work anticipating pedestrians crossing with future frames prediction. So here we introduce our work with a real life and uncertain situation where a pedestrian is standing at a crossing point and may or may not cross in front of the vehicle. As a human drivers, so we predict pedestrians' actions through nonverbal physical communication, such as eye contact, as in this example. This eye contact is then understood by the driver, who slows down and then let the pedestrian cross in front of the vehicle, as we can see in these next frames of the same video. Our work focuses on the understanding and anticipating of pedestrians' actions as a step towards fully autonomous driving vehicles capable of understanding such nonverbal communication. Our proposed approach is end-to-end model that operates in 2 stages. The first stage is a future frames prediction model, which is encoder-decoder network that operates in unsupervised manner to predict the n future frames of a video given the n initial frames. Our encoder is composed of 3D convolutional layers, and our decoder is composed of conv LSTMs interspersed with upsampling layers. The second stage of our model is a deep spatio-temporal action recognition network that utilizes the generated video frames to predict the pedestrian action. But our full model is end-to-end trainable with the multitask loss function where both tasks are trained jointly. So here we show the performance of our future frames prediction component, where we can see in this plot on the vertical axis the frame by frame L1 loss, which is computed on the test data. And here it's clear that our approach performs better than the state-of-the-art methods for future frames prediction. And here we show the evaluation results of our end-to-end model for pedestrian crossing action prediction. And we can see that our model outperforms state-of-the-art methods. And also we can see the effect of the joint training into further improving the performance of our model. And finally, I will leave you with some examples of future frames prediction, as well as the predictions and the ground truth of the pedestrians' actions. If you are interested into more details about our work, please come and see us in poster session. Our poster number is 48. Thank you.
Okay, hi everyone. My name is Mateusz, and I have the privilege to present this work to you. Postmortem iris recognition that is resistant to biological eye decay processes. And this is a joint work of 3 institutions. I'm with the NASK National Institute in Poland. Adam is with the University of Notre Dame, and Piotr is with the Medical University of Warsaw, so in Poland. So, right. As for the postmortem iris recognition, this can be really useful, for example, to identify the victims of mass catastrophes. But the problem is that it really doesn't work very well with current state of the art. And in this slide, I've put up an ROC-wise performance, for example, for the OS-Iris open source iris recognition method, the commercial state of the art, the iRecord, and it's quite bad. And what we've tried to do with this in our previous research is to apply some custom deep learning based segmentation of the iris images, and that helps a lot. That's a black curve, and that was applied to the OS-Iris. But as you can see, there's still some room for improvement in the feature representation domain, maybe. So what we tried to do is to learn iris-specific filters, and we did that by employing this CME's CME's network with just 1 layer of convolutions that is fed with imposter and genuine patches of irises, and is supposed to produce filter kernels that are optimal for this kind of task, namely recognizing postmortem irises. And what the network gave us, we then tried to optimize with a traditional Gabor filters that were used by Dagman, for example. And that was done using the sequential feature selection, and that allowed us to create sort of a hybrid filter bank that comprises of a Gabor wavelet component, the blue one, the 4 wavelets, and the iris-specific components are the yellow one. And what this allows us to achieve is that we have an additional red curve now that is far above the black one, and what it allowed to do is to cut the error rates by almost 1/3. So that's quite good. Of course, there's still some room for improvement, or maybe there isn't, because what's left there is just postmortem decay of the eye, and some of the features of the iris are lost forever. so thank you for listening. Please stop by the poster number 48, 49, or 50, depending on the version of the program that you have. So, yeah, thank you.
So, good evening, everyone. My name is Lukáš Picek, and today I would like to introduce to you a joint project between the University of West Bohemia, Czech Technical University in Prague, University of Copenhagen, and the GBIF. And the project is focused on the usage of automatic fungi recognition for the citizen science project. Since data are important for the further research on biology, especially in areas such as biodiversity, climate change, and species extinction, our main motivation was to build a system that will provide us endless and costless stream of data necessary for mycologists to continue in their research. But how to achieve that? Since the 50% of the data in the GBIF database comes from the citizen science projects such as iNaturalist, Birdwatch, Wildbook, etc., involvement of such community is then a reasonable step that might bring us a cost-effective approach to the large-scale data collection. But how to motivate a user to contribute to such kind of project? We decided to build an AI-powered application for all the platforms, including iOS and Android, and integrates the photo recognition system based on our winning submission to the CVPR FGVC Fungi Recognition Challenge that is actually served with the help of TensorRT and TensorFlow. What was actually the contribution of such integration? On the first 6,000 records, we measured that 84% of the classes proposed by the recognition server were approved by the expert or the community itself. As far as I know, this accuracy is way better than the most non-expert users could have. Based on that, we received positive user feedback, and even the Danish mycologists were highly impressed by the performance of the system. So how the system contributed to the data collection? We measured that the system almost doubled the number of active users, and at the same time the number of submissions to the Danish Fungi Atlas. And that's a really impressive number. Okay, now let's move to the video showing the usage of the mobile and the web application. As you can see, user might take a picture or to select the picture from the gallery, and almost immediately he receives the top 5 most similar species related to the given image. This works as well for the web application. And that's actually all from me. So thank you for your attention, and see you at the poster session where you can test your own mobiles on the pictures I have there. Thanks.